8 homework. I already recorded a video and posted on the Blackboard yesterday. So today, after this explanation quiz 7, we'll complete chapter 8 very soon. If some time left, we'll start chapter 9. Quiz 7, question 1. A asks you what is the wavelength of light having frequency 3.2 times 10 to the 12th power hertz. Ask you what is the wavelength. So in this chapter, at the beginning of this chapter, all about the knowledge about a wave, right? So wave, we have basic equation is frequency times wavelength equals to speed, and the light speed c equals to 3 times 10 to the 8th power meter per second. I provide this number to everybody, right? So clearly wavelength should equal to c divided by frequency. So c is 3 times 10 to the 8th power meter per second. Wavelength frequency is 3.2 times 10 to the 12th power hertz. Hertz, the actual meaning is per second. So cancel this per second. Leftover meter. Right. Use your calculator. This is many times I tell everybody. Use your calculator just for this regular number. Okay. Don't put exponent in the calculator. This make you trouble. So 3 divided by 3.2 will be 0.94. Exponent, they're very easy. Division, exponent, subtract. So 8 minus 12. Right. Since this 0.94 is less than 1, right? Scientific notation requires this is greater than 1, less than 10. So we need to move 1 decimal place. Becomes 9.4. You move 1 decimal place, you enlarge it 10 times. Then we need to get it back. So minus 1. So this is negative 4. Then minus 1, negative 5. Right? The unit is meter. Okay. You can keep this answer. Or if you want, you can convert it to nanometer times 10 to the 9th power. So this should be positive 4 nanometer. Are you okay for this? Okay. And B, this time tell you wavelength lambda is 450 nanometer. As you calculate frequency nu, then you switch wavelength with frequency, right? So c divided by lambda is frequency. So c is same, 3 times 10 to the 8th power meter per second. Wavelength 450 nanometer. So you need to be careful. You cannot use this directly because this nanometer, this meter, you cannot cancel them. Okay, so you need to convert a nanometer into meter. So meter here, nanometer in bottom. So nanometer cancelled, leftover meter. This meter then cancel this meter. Leftover per second. The meaning is hertz, which is a unit for frequency. Then 1 nanometer, 10 to the negative 9th power meter, right? Nanometer cancelled, meter cancelled, leftover per second, which is hertz. Then mathematically, negative 9, we can move this 3 decimal place becomes 0.45. 0.45, then 3 divided by 0.45. 3 divided by 0.45 is 6.7. If move 3 decimal places, you have 10 to the third power. 10 to the third power combined with -9, you still have 10 to the -6. And this in denominator, the minus -6 is plus 6. So 8 plus 6 is 10 to the 14th power. So this is your answer for the frequency. So these two, if you know one, you should know the other one. This is very similar, right? So question 2. A asks you how many electrons can be placed in 3D subshell. 3D subshell, how many orbitals? Always 5, right? D, always 5 orbitals. 3D, 4D, 5D, 6D, always 5 orbitals. Each orbital maximum can place 2 electrons, then total 10 electrons, right? This is very clear. So 10 electrons. B asks you the number of orbitals in a p subshell. P always 3 orbitals, right? S subshell is 1 orbital. 1s, 2s, 3s, always 1 orbital. P always 3 orbitals. 2p, 3p, 4p, 5p, always 3. D always 5, right? So this is a 3. So you need to read these questions carefully. Some of you feel this is 6. This is no 6 orbitals for any subshell. I'm assuming you didn't read this carefully. You think this is the number of electrons in 3 in p subshell could be 6. Right? 3 orbital. Each orbital fell into total 6 electrons. But here also your orbital number is 3. Okay. Question 3 asks you what is the orbital diagram for ground state nitrogen? Okay, take a look at the table. For nitrogen, how many electrons for nitrogen? This is 3. Okay. Nitrogen is here, right? 7. 7 protons, 7 electrons. Right. Then we can write electron configuration. For nitrogen, we can write electron configurations 1s2, 2s2, then 2p. How many electrons here? Total 7, we already have 4, then only 3 left, right? So you only have 3 left. Then what is the orbital diagram? So this is 1 orbital, 2 electron. 1 orbital, 2 electron. 2p, 3 orbitals, right? 3 orbital, according to Horner's rule, this 3 electrons should be in each orbital. And same spin direction, or clockwise or anti-clockwise, either way is fine. So you draw one line for each orbital, or you draw a box for each orbital like this. Without a line or box, nobody can understand What it means? Some of students write like this way. All stick together. Nobody can understand what this means. Okay. You need a fair electron in each orbital, either a box stand for orbital or a line stand for orbital. And this electron configuration align with this orbital diagram. So the other body can understand, oh, this is 2s and this is 2p. Okay. So what is the answer for this one? Clearly, this is rule 1, same as this, right? We need to switch it to many problems for this question 4. Many mistakes. Also, you write the electron configuration and draw orbital diagram for the following element. So A is calcium. So first of all, you need to use periodic table to find out how many electrons. For calcium, how many electrons? So clearly it's 20. Right? So 20 electrons. And you need to use this chart. So 1s first, then 2s, 2p, 3s, 3p, 3d. D starts here 3. Then 4s, 4p, 4d. So 1s lost, then 2s, then 2p, 3s, then 3p, 4s. Followed by 3d, 4p, 5s. According to this order, so we can write electron configuration. So place 2 in 1s order, 2 in 2s order, then 6 in 2p order. Total 20, now only 10. So we still have electron. Then 3s, 3p. Right. So we need to leave some, we need to leave more space to draw orbital diagram. Okay. 3s, 3p. Now it's 18, right? Now we have 3p is 4s, 2. Now it's 20. Now draw orbital diagram. So draw one orbital under this 1s. And 2s also one orbital. 2p, 3 orbitals, 6 electrons. Each orbital fills 2. 3s is 1 orbital. 3p also 3 orbitals. Then 4s, 1 orbital, 2 electrons present. So align this s with this is name with the orbital. Okay, this 2s, this 2p, this 3s, this 3p, this 4s. Without this electron configuration, if you only draw this alone, nobody can understand. This could be understood as 2p or 3p or 4p, right? You need to align your electron configuration with the orbital diagram. Then other body can understand what you wrote. Okay. So B, copper. With the help of periodic table, how many electrons for copper? Copper is here. 29 electrons, right? So 29 electrons. Then we can write electron configuration according to this chart. So 1s2, 2s2, 2p6. We need to leave some space because 2p have 3 orbitals. need to leave more space. Then 3s2, 3p6, followed by, we need more space here. Right, let me write like a lower name. So copper 29, 1s2, 2s2, then 2p6, then 3s2, 3p6. Now here leave 4s2, that's 20, right? Then left over 3d, only 9. So when you see 3d9 or 4d9, you need to think about this full figure. Pour 1 from its neighbor S and place on the D becomes D10. Okay, this is a special case. D9 becomes D10, D4 becomes D5. This extra electron comes from its neighbor S orbital. Again, this rule only applies to D orbital, not applied to other P orbital. So we never say P5 becomes P6. Okay. Only apply to D orbital. The full field, more stable. So this is electron configuration. Now we can draw orbital diagram. 1s is a 1 orbital. 2s also 1 orbital. 2p 3 orbitals. 3s 1 orbital. 3p 3 orbitals. 4s, be careful, only 1 electron. Then D, you have 5 orbitals. Powerful. An electron. Place 2 electrons in each orbital. C, chlorine. I use periodic table. Chlorine 17 electron. Then still use this chart. So 1s2, 2s2, 2p6, 3s2. Or 5 left, then 3p5. Okay, so this your orbital diagram is similar. So 2 electrons in 1s, 2 electrons in 2s, 2p, 3 orbitals. Place 2 electrons in each orbital. 3s, 1 orbital, 2 electrons. 3p, 3 orbitals, 5 electrons. Place 1 in each orbital first. Then you need to pair 2 of these orbitals. Left over 1 orbital unpaired. And last one is iron. From periodic table, we know iron has 26 electrons. Then we can write electron configuration still according to this chart. So it should be 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2, 3d6. Let's try. 10, 20 plus 6. D maximum can place 10, but only 6 left. Right, so this D6. Draw orbital diagram. 1 orbital in 1s. 2s also 1 orbital. 2p 3 octets, 3s 1 octet, 3p 3 octets, 4s 1 octet, and 3d 5 octets. 5 octets, 6 electrons. Place 1 electron in each octet first. Counter's rule requires same spin direction. Then you have one more. One more you can place in any one of these 5, but the opposite spin direction. Okay. Are you okay with this? Question 4. We have one special case. All other 3 just use this charge. Then question 5. I remember before quiz, the class before quiz, I gave a very similar example. Actually, it's from homework. 2 energy level of a hypothetical atom E2 is negative 10 times 10 to the negative 19th power joule. E1 energy level is negative 18 times 10 to the negative 19th power joule. The question is, ask you what is the energy in joule a photon must have in order to excite an electron from E1 to E2. Electron initially in one level of the energy level is E1. Okay. Once excited to E2, ask you how much energy needed. Of course, energy needed is energy difference between these two, right? This energy needed is energy difference between these two, and the difference always final minus initial. From here to here, of course, this E2 is a final. We have several E1 minus E2. So the energy change always a final minus initial. Volume change also final minus initial. So energy change always a final value minus initial value. And here ask you electron excited from E1 to E2. Which one is the final? Of course, E2 is the final, right? So E2 minus E1. E2 is negative 10 times 10 to the negative 19. And the E1 is negative 18 times 10 to the negative 19. So minus negative 18 plus 18. The 18 minus 10 is 8. 10 to the negative 19 is the power. Both numbers same, right? Subtraction, addition requires exponent and same. It's already same, right? So this is the energy needed to excite the electron from E1 to E2. Energy difference between these two. Then B, ask you what is the wavelength of the photon needed to excite the electron from E1 to E2? This is actually the same question, just ask you second answer. So excite electron from E1 to E2 level, you need this amount of energy. This energy comes from a photon. It's light. Right? So energy from a photon equal to h times nu. But here ask you wavelength, not frequency. Then we need to convert this into wavelength. Nu equal to c divided by lambda. Question 1, right? So E we already calculate. H is a Planck constant provided here. C light speed also provided. Can you calculate the wavelength? Yeah. So wavelength equal to h times c divided by E. Okay. The h Planck constant top of this sheet 6.63 times 10 to the negative 34th joule second. C is the light speed, also provided here. So 3 times 10 to the 8th power meter per second. E is the energy needed. We just calculate is 8 times 10 to the negative 19th power joule. Okay. So now you find second, cancel this per second. Okay. Joule, cancel this joule. Leftover meter. This is the unit for wavelengths. The number, just use calculator. Put this regular number 6.63 times 3 divided by 8. This gives you 2.49. Exponent, don't put in the calculator. So multiplication, so plus negative 34 plus 8. Division is minus negative 19 equal to plus 19. So 8 plus 19 is 27. Negative 34, then negative 7. And you can stop here because I didn't specify must be in nanometer. You can stop here. If you want, you can convert it to nanometer. 5 times 10 to the 9th power. 9 minus 7 is 2. 2 move 2 decimal place. You don't have to because I didn't request you. I didn't answer with nanometer. Are you okay with this? Do you have any question for this quiz? Okay, if you don't have question